So this lesson is going to show you how to calculate two very important variables. The first is the respiratory exchange ratio. And the second is relative oxygen consumption, or relative VO2. So we'll begin with RER. Now the metabolic cart, as we learned, measures the amount of oxygen that we breathe out, the amount of CO2 that we breathe out, and the expired air we breathe out. And by comparing that to room air, we can figure out our oxygen consumption, how much oxygen has been consumed by our metabolism inside our bodies. We can also calculate how much CO2 has been produced. So whenever we burn a fuel in our body, we require the consumption of oxygen, and as a byproduct we produce water and carbon dioxide. And that carbon dioxide has to leave our body. So it leaves our body, starting in our cells, into our bloodstream, and then from our bloodstream to our lung, and then we exhale that air. So before we get to RER, at the level of the cell, and you must remember this, we have what's called respiratory quotient, which is the same as RER in terms of how you calculate it, but this one we cannot measure accurately in one cell in the human body. So what we measure is respiratory exchange ratio, which is the level of the lung, which is a measure of the metabolism throughout the entire body. There's one important difference between these two, which I'll come back to later on, which is that RQ does not exceed 1. So RQ can be as high as 1.0, but no higher. Whereas RER, whole body metabolism, the number can be larger than 1. So how do we calculate these? Well, let's take an example during light exercise. Let's say we're producing 0.86 liters per minute of CO2, and we are consuming 1.08 liters per minute of oxygen. Well, the formula for RER is quite simple. It's CO2 produced over oxygen consumed. So here we would have 0, I'll do it in red, .86 divided by 1.08, and all the units will cancel, and we're left with a number, in this case 0.80. So as I mentioned, the number cannot exceed 1 for RQ, but it can exceed 1 for RER. But the range, you'll see here, is anywhere from 0.7 to 1.0, and then greater than 1. At 0.7, an interesting fact is that you're burning almost completely fats. And at a ratio of 1.0, you're burning almost completely carbohydrates. So let's take a look during heavy exercise where these numbers are going to increase. So during heavy exercise, we're producing a lot more carbon dioxide. In this case, let's assume we're producing 5.03 liters per minute of carbon dioxide, and we are consuming 4.45 liters per minute of oxygen. So heavy exercise, this would be the end of a graded exercise test. If we do the math, we discover that 5.03 divided by 4.45 is equal to 1.13. Here's an example where now we've exceeded 1.15, let's say. So within our range of RER, those are three important numbers to remember. So measured as whole body metabolism, if your RER is 0.7, you're burning complete fats, you're doing very light exercise, maybe even just sitting in a chair. As your RER approaches 1, you're on the boundary of the anaerobic threshold, and your body is almost completely burning sugars. And when your body is at heavy exercise, you're above the anaerobic threshold, you produce a greater amount of CO2 because of the addition of that anaerobic metabolism, and your RER can climb above 1. And 1.1, sometimes 1.15 is a criteria for VO2 max. 1.0 is an estimate, a rough estimate of the anaerobic threshold. So there's another important thing we can do here that's often done with oxygen consumption, which is to turn these numbers into a relative amount. So why is that important? Well, right now, the unit is liters per minute. But 4.45 liters per minute doesn't tell us a lot about the person. So if we know the mass of the individual, let's say in this case it's 80 kilograms, we can figure out a relative amount. So we take the absolute amount, we convert it into milliliters. So we multiply this by 1,000 millimeters per liter, and we divide that by the body mass of 80 kilograms. And in this case, during heavy exercise, we would get a number of 5.6 milliliters per kilogram per minute. Now, how does that happen? Let's just take a quick look at the units. Well, here, liters cancel. Okay, minutes are on the bottom, so we're left with mils per kg per minute. So to convert from absolute to relative, you multiply by 1,000 and divide by body mass. This number is much more normative. If you're comparing athletes, generally that's expressed in this number. If you're looking at a health standard, generally VO2, oxygen consumption, is expressed as relative. It's also more important in sports, where you must carry your body mass. Because as this number decreases, your oxygen consumption in relative terms increases. So small athletes like marathon runners will have a larger relative VO2 if their body mass is smaller. Versus athletes where carrying their body mass doesn't matter as much, for example, a rower, where the absolute number just describes the size of their aerobic engine, which might be more important to that event.